In today's lecture, I want to continue with Chapter 1 from your carry text. We're going to discuss sections 1.5 and then 1.9 through 1.11. The key concepts of today's class can be illustrated in a handful of examples. So I have 5 different chemical formulas here, and I want to walk through each of these different concepts with each chemical formula. The first molecule that I'm going to look at is formaldehyde. We saw formaldehyde in the previous lecture, so I already drew the Lewis structure for that compound. It follows the Honk-X rules. The Honk-X rules tell us that hydrogen makes 1 bond and has 0 lone pairs. Carbon tends to make 4 bonds with 0 lone pairs, and oxygen makes 2 bonds with 2 lone pairs. Once we've determined the Lewis structure for the compound, then we need to move on and talk about the hybridization of the individual atoms. The hybridization of atoms is a way of trying to explain why they behave the way they do. If we think about hydrogen, it has 1 electron that it brings to the table. The electron that hydrogen has typically resides in its ground state or lowest energy position in the 1s orbital, 1s. And this is an orbital notation diagram, and hopefully you've drawn a few of these in the course of your experience in general chemistry. And in this orbital notation diagram, we show the shell, which is the first shell, the subshell, which is either S, P, D, or F, and we identify that that subshell has 1 spot to put electrons, that's called an orbital, and the electrons are going to be either spin up or spin down. So if you have a single electron, and this is what hydrogen has, then its ground state or lowest energy state would be to place that 1 electron in the 1s subshell in the only orbital, and it's going to have some orientation. If we move from hydrogen to helium, then now we're going to add a second electron to the system, and that electron will add into that same 1s orbital, and it will have an opposite spin state, so we show an arrow going down, and this is the orbital notation diagram for an atom of helium. Going back to hydrogen, in an atom of hydrogen you have an orbital that is half filled. A bond is best described, for the sake of the molecules that we're going to look at, as the overlap between 2 half-filled orbitals. So hydrogen makes 1 bond because it can use this half-filled orbital and overlap with a different atom to make a bond. Let's look at what that, let's see what that looks like with carbon. Carbon has 6 total electrons. So we're going to draw little lines here. This represents right here the 1s orbital for carbon, the 2s orbital for carbon. Once you fill up that 1s orbital, then you've filled up your entire first shell. And so we move up to the 2s orbital, and I'm showing it vertically a little higher just to remind myself that it has a higher energy state. So we'll go ahead and put some electrons in here. Carbon has a total of 6 electrons. There are 2 electrons that are in the inside shell. Those are not valence electrons. That means that carbon has the remaining 4 electrons are all valence electrons. We put 1 in the 2s orbital, and we put the other 1 in the 2s orbital. We still have 2 electrons to place. Those electrons end up going into the 2p orbital. The 2p subshell. The 2p subshell has 3 separate orbitals. It is common to refer to them as 2px, and then we have 2py and 2pz, but not absolutely required because x, y, and z the atoms don't really have any inherent internal axis, and so this is just for us to differentiate them. Okay, so the p subshell has 3 different orbitals, and carbon is going to place 2 electrons inside of this p subshell. The first electron can go anywhere. All 3 of these orbitals are equivalent in energy, and so it doesn't really matter where you put it. We like to work from left to right, so let's start there. Once you put the first electron in there, now the second electron has to respond. Electrons don't like to occupy the same orbital unless they have to. So the second electron is not going to fill this first orbital, the 2px. if there are open slots in 2py and 2pz. So instead it's going to come over here. And the second thing is that electron will have the same spin as whatever other electrons are in the same subshell. So it'll be either in 2py or 2pz, but it definitely is going to be spin up. If we go from carbon to nitrogen, we add nitrogen has an additional electron. It's got to go in the last open slot. And then when we get to oxygen, we have another electron. That's the next element on the periodic table. And so that's finally when the electrons have to start doubling up. And so I'm going to add an electron to any one of these three orbitals. It doesn't matter, but we like to work from left to right, so I'll put it here. And finally, this electron now pairs up. So this is actually the orbital notation diagram for oxygen, which is going to matter in just a second when we talk about oxygen. But we started off trying to figure out the orbital notation diagram for carbon, so let me draw that. Copy and paste this structure. I don't know what this line's doing right here. And so to do carbon, let's go ahead and put the carbon in there. And we'll get rid of 2 electrons. So we'll get rid of this electron right here and then that electron. So here is our diagram for carbon and our diagram for oxygen. And this is what they look like before they make bonds. So this is kind of an arbitrary diagram because it assumes that we're talking about an atom of oxygen or an atom of carbon or an atom of hydrogen that exist all by themselves. And if you've learned nothing else from general chemistry, it's that atoms tend to make bonds. And so an atom of carbon doesn't actually exist in a very stable, this isn't a stable configuration. It will, if you put it with anything else, it will immediately start to bond, even with itself. And so oxygen tends to make O2 as a diatomic, hydrogen makes H2, and then carbon actually makes a combination. If it's all by itself, it will start to pair up, actually more than pairs. You get rather complicated carbon structures. And the goal is for all of these atoms to ultimately achieve a noble gas configuration. We often call that an octet, and that makes sense for oxygen and carbon when they want to have 8 electrons here in the second shell. To say that hydrogen has an octet is kind of goofy because hydrogen actually only wants to be like the nearest noble gas, helium, which has 2 electrons, so hydrogen's octet is actually a doublet. Hopefully now you're starting to realize there's a problem. I've defined a bond as the overlap of half-filled orbitals. And if you look down here at carbon, carbon only has 2 half-filled orbitals. And so if carbon is to make bonds, we would expect, based on this orbital notation diagram, that carbon would only be able to make 2 bonds. It would form a bond between the 2px, and it would physically overlap in space with the 1s orbital of hydrogen. That would form a bond between the carbon and the hydrogen, and then another hydrogen would come in and bond with the 2py. And that would be it. The molecule would be CH2, and that would be all that carbon could do. But from the Honk X rules, we learned that carbon has a tendency to make 4 bonds. So now the question is, how does it make 4 bonds? And the answer is hybridization. So this orbital notation diagram for carbon is correct if carbon is all by itself in a vacuum, like in space. As soon as carbon enters the real world and starts to interact with other elements, then it takes and shifts this diagram. So now I'm going to do a couple things here. First of all, only the valence electrons matter. And so these 1s electrons right here don't matter to us because they are not valence electrons and they're out of play. The way that we got away with not showing those electrons in general chemistry was they call this the noble gas notation, where you say that carbon is everything that helium is plus anything that I'm showing you. So that's kind of an abbreviated way of getting rid of the diagram that we don't want. So what happens during hybridization is that the carbon takes all these electrons and kind of sets them off to the side. It's not, I'm kind of imagining that this is what's going on. We really don't have a model for this, of how this process happens. We just know what it looks like to begin with and what it looks like when it's done. And then it takes these 4 orbitals right here, or some number, we'll assume 4 in this case, and it just throws them in a blender. And the purpose of blending up those orbitals is that now what we end up producing are 4 orbitals that are all energetically equivalent. They're all exactly the same. Now, spatially, these 4 orbitals are all extending away from each other. We'll talk about the spatial orientation in just a second. But they're now no longer s and p orbitals. They're not s and they're not p. They are a hybridized version of that. And since we took one s orbital and 3 p orbitals and we put them in our blender, they refer to this as an S1 P3 hybridization. Oops, P3. And then we decided, well, one's kind of tedious to say and it's kind of assumed because the letter S is there's one of them. And so the hybridization is referred to as SP3. And let's go ahead and make that a superscript so that it looks a little bit more familiar to you. This is an sp3 orbital right here. This one is also an sp3 orbital, etc. So all 4 of these are now referred to as sp3 orbitals. And we've taken our carbon and we've turned it into a hybridized version of carbon that is sp3 hybridized. Now technically we should call this the 2sp3 and this should be the 2sp3, and because we took s and p orbitals from the second shell. If we were hybridizing an atom on a different row of the periodic table, such as silicon, then it would be 3sp3 instead of 2sp3. But for whatever reason, they just kind of left those numbers off, and we don't generally tend to show those, even though I argue that we should. Once we've made these 4 equivalent orbitals, then we put those 4 electrons back in again. And so, oops, it's hard to grab these things, so I'm just going to redraw them. Let's go back and select my arrow tool. So these 4 electrons, 1, 2, 3, and 4. And notice how, whoa, all 4 of these electrons end up in their own orbital. They all have the same spin state, and this is how carbon can make 4 separate bonds. And this is the type of orientation that we would expect if we're talking about a compound like methane. So methane has a carbon with 4 separate bonds coming off of it, like this. All 4 of those bonds are made between an sp3 hybridized orbital of the carbon, and an hydrogen can't hybridize. It doesn't mix up its s and p's because it only has s's, so the hydrogen just ends up being a 1s orbital. So we have the 1s orbital of the hydrogen interacts with the sp3 orbital of the carbon. Okay, so this is what happens with methane. It's not actually what happens with formaldehyde. And so the reason is that while this carbon is definitely making 4 different bonds, we also have to think of something called electron groups. Hybridization is ultimately dictated by electron groups. Electron groups are equal to bonded atoms or lone pairs. So what that means is that this hydrogen right here has 1 electron group. It has 1 bonded atom. It's bound to the hydrogen, so it has 1 electron group. This hydrogen over here also has 1 electron group. The carbon has 3 electron groups. It has a bonded atom to this hydrogen, a bonded atom to this hydrogen, and a bond to this oxygen right there. So electron groups actually refers to single, double, and triple bonds as just 1. This oxygen right here has 3 electron groups. It has a bonded atom to the carbon, and then it has a lone pair here and a lone pair right there. So that's 3. So the number of electron groups is how we predict the hybridization. For this carbon right here, it has 1, 2, 3, 4 different bonded atoms, so it has 4 electron groups. And there's a chart that I made that counts, here's the number of electron groups that a compound has, and then there, written off to the side, is the corresponding hybridization. Anytime you have 4 electron groups, the hybridization is sp3. If you have 3 electron groups, it's sp2, and 2 electron groups is sp. If you have 5 or 6 electron groups, those are hybridizations that we simply don't encounter in organic chemistry. And so this portion of this diagram right here, it's a picture, it's not an Excel file. Only the top half of this is relevant to organic chemistry. The bottom half of this I pulled from my notes from teaching general chemistry. So organic chemistry on top, and then the full table was something we talked about in general chemistry. Inorganic chemistry, which is a lesser science, uses this bottom chart right here, and we don't care about that. So going back to this carbon right here, it has 1, 2, 3 electron groups, and therefore it is sp2. 2 hybridized. That's how I read that chart. If you have 3 electron groups, then the hybridization is sp2. Well, what does that mean? Well, let's get rid of methane, since the question didn't actually ask us about methane. If you are sp2 hybridizing something, then instead of grabbing all 4 of these orbitals and sticking them in the blender, sp2 means that you're taking the s and 2 of the p's, and that's what you're putting inside of your hybridization blender. And so the resulting output of that is that these 3 orbitals right here are now equivalent to each other, and that 2pz orbital that we didn't put inside of the blender, it survives unscathed and just kind of sits over here. And so these orbitals down here are referred to as sp2 orbitals, and there's 3 of them. So I'll superscript that. And then rather than write sp2 on all 3 of them, I'll just put a label down here that says that these 3 are sp2s and this is 2pz. And now we can take and put 4 electrons in the system. There's 1 electron here, 1 electron here, 1 electron here, and the 4th electron goes into this 2pz orbital. And this is how the carbon ends up making 3 bonds with its sp2 orbitals that are single bonds, and then any pi bond or any secondary bond ends up being between involving these unhybridized 2pz orbitals. So now you should be able to answer the question of what is the hybridization of the oxygen based on the number of electron groups. Pause the video, see if you can come up with an answer, and then restart the video, and you'll see if your answer matches mine. Let's see how you did. What we want to do is show the hybridization using this oxygen diagram right here. As I illustrated before, we don't care about the electrons that are not part of the valence shell, so I'm just going to pick up from oxygen, use my correct orbital, noble gas notation, where we say oxygen is everything that helium is, plus this. Oxygen has a lone pair, that's 1 electron group, another lone pair, that's your 2nd electron group, and a bonded carbon, 3 electron groups. Anytime you have 3 electron groups, then your hybridization is sp2. So oxygen grabs the s orbital and 2 of these p orbitals, and is going to convert that into the same diagram we see down here. It's an sp2 diagram, so just like this. So oxygen's doing exactly the same thing that carbon did. Only the difference now is that oxygen actually has 1, 2, 3, 4, 5, 6 electrons to place in here. And electrons tend to fill up. Electrons are lazy, and so they will fill up the lowest energy orbitals first before they move over to the higher energy orbitals. Where is my curved arrow? There it is. All right, so that means that when we put oxygen as 6 electrons, 1, 2, 3, and then it's going to add the electrons in here, 4, oh, that's kind of ugly, 5. And then the oxygen is going to leave this electron right here in a half-filled orbital so they can make one of these bonds. The single bond, the first bond between the carbon and the oxygen, involves this hybridized orbital. And this is going to take the other electron and put it up here. And this allows the oxygen to make an orbital overlap between the unhybridized 2pz orbital of the oxygen and the unhybridized 2pz orbital of the carbon. So now hopefully you can kind of see how this is all going to connect together, the pieces that we have. The hydrogen takes its 1s half-filled orbital and sticks to the sp2 hybridized orbital of one of the carbon. Another hydrogen on this side takes its 1s orbital, sticks to another one of the hybridized sp2 orbitals of the carbon. And then the sp2 orbital of the oxygen bonds to the last sp2 orbital of the carbon, and then the 2pz's between the carbon and the oxygen line up to make that double bond right there. Okay, the point of all of this was to get you to look at a Lewis structure and start to predict the hybridization. You could actually ignore all of this and just memorize that if the carbon has 1, 2, 3 things coming off of it, then it's sp2. If the oxygen has 1, 2, 3 electron groups, then it's also sp2. And that's really what the question is trying to get you to see. I was trying to give you an explanation for the hybridization and where it comes from. Okay, now that we've assigned hybridization to the carbon and the oxygen, let's talk about geometries. This table right here actually tells you what the geometries are. If you have 3 electron groups, then your hybridization is sp2, and your electron geometry is trigonal planar. Trigonal planar means that you have three different things coming off of a central atom that all exist in the same plane. If there are no lone pairs on the central atom, then the molecular geometry ends up being the same. So going back to this diagram right here, this carbon right there is the central atom. It has 3 electron groups and is therefore sp2 hybridized. Those 3 groups are going to push away from each other as hard as possible. This is the concept of VSEPR, which is a mispronunciation of VSEPR, which stands for valence shell electron pair, valence shell electron pair repulsion theory, VSEPR. VSEPR just tells us that electrons will try to get away as far away from each other as possible. So this bond right here and this bond are going to try to get away from each other, and that bond's going to try to get away from the other two, and they end up forming a triangle where all 3 of them extend outward from the carbon in the same plane, and the bond angle between the carbon-oxygen here and the carbon-hydrogen here is about 120 degrees, okay? Because it takes 3 120 degrees to add up to 360, which is your circle. So the electron geometry of the carbon is if it's sp2, it's always going to be trigonal planar, and if there's no lone pairs, then the molecular geometry of the entire molecule stays the same. It's also going to be trigonal planar. Let's look at a different molecule, this CH2Cl2. This thing is called methylene chloride. We're going to use that quite a bit in the laboratory as a solvent. So I need to get rid of all of this. Using Honk-X rules, CH2Cl2 tells us that we've got a carbon. It's going to go in the center, and there's going to be 4 things around it. So this is the carbon right here. This is a hydrogen, hydrogen, chlorine, chlorine. And the Honk-X rules tell us that hydrogen makes 1 bond and has no lone pairs, so they're good. Carbon makes 4 bonds with no lone pairs, and the halogens, X, tend to make 1 bond and have 3 lone pairs. So clean that up just a tad, and then we'll go ahead and dump the lone pairs on the chlorine. 1, 2, 3 lone pairs. 1, 2, 3 lone pairs. All right. Here is my Lewis structure for CH2Cl2 or methylene chloride. The carbon is the atom in the center, has 4 bonds. Therefore, it has 4 electron groups. So 4 electron groups equals sp3 hybridization, and that is tetrahedral electron geometry. When you have 0 lone pairs on the central atom, in this case the carbon, then your electron geometry and your molecular geometry are the same. That's always the case. If you have 0 lone pairs on the central atom, which in this case is carbon, then your electron geometry and molecular geometry are the same. So this is sp3, the geometry is tetrahedral, and the molecular geometry is also tetrahedral. The next one is CSO, so we'll go back to ChemDraw. That's going to put a carbon in the center. We have an oxygen on one side, and we have a sulfur on the other side. Oxygen's tendency is to make 2 bonds and have 2 lone pairs, so we'll go ahead and put the 2 lone pairs on the oxygen right here. Carbon tends to make 4 bonds with no lone pairs, so we've got 3 bonds shown, so let's go ahead and drop the 4th bond in there. And sulfur doesn't really have strong tendencies, but if it can act like oxygen, it will. So 2 bonds, 2 lone pairs. They're in the same column of the periodic table. The whole organization of the periodic table is to try to put things that are similar in same columns, so it makes sense. So this compound, I forget the name of this compound. It's kind of difficult to make, not super stable. But anyway, this is the Lewis structure. The hybridization of the carbon. So there are 2 electron groups on the central atom. And anytime you have 2 electron groups, then your hybridization is sp, and the geometry is going to be linear. So you have linear electron geometry. There are 0 lone pairs on the central atom, which is true in this case because carbon is the central atom. Then your electron geometry and your molecular geometry are the same, so it's also linear. Easy enough. Next one. SO2. This is not an organic compound, so we have to be careful using the Honk-X rules. I'm going to put sulfur in the middle. and I've got an oxygen on each side. So here's an oxygen over here and an oxygen over here. The total number of valence electrons, I need to count that up. So sulfur has 6 valence electrons, so do both oxygens. So that's 18 total valence electrons. I've spent 2 here and 2 here making the bonds, so I'm down to 14 valence electrons left. I'll put 2 there, whoops, 2, 4, 6, 8, 10, 12, 14. I've spent all 14 of my valence electrons. Notice here that the sulfur does not yet have an octet. It only has 2, 4, 6 electrons. So I'm going to take one of these lone pairs off the oxygen. I'm going to drag it down as a double bond between the oxygen and the sulfur. So here is, whoops, ChemDraw does not like this particular resonance structure, and you shouldn't either because of formal charges. If we add up the number of valence electrons that sulfur is supposed to have, remember that formal charge is equal to the number of valence electrons minus the sum of lines plus dots. Oops. So for sulfur, so the formal charge of the sulfur is equal to 6 valence electrons minus the lines that sulfur has, which is 3, plus the dots that it has, which is 2. 6 minus 5 is equal to positive 1. And the formal charge of the oxygen over there on the left-hand side is equal to 6 valence electrons minus, we have 1 line plus 6 dots, so 6 minus 7 is equal to a negative 1. So this particular structure that I've drawn is a resonance structure where the oxygen has a negative formal charge and the sulfur has a positive formal charge. And like I said before, anytime you have negative formal charges adjacent to positive formal charges, you should be able to take a lone pair and drop it down into a bond like this, and it gets rid of the formal charges. So I'll make a double bond here, and now ChemDraw's mad at me again because of the formal charges, so I get rid of those. And there's our structure. And this is a better resonance structure because I have eliminated my formal charges. Also, I have expanded the octet for sulfur. It actually has 10 electrons here, which is allowed. Remember, any element in the third row or down can go above and beyond the octet if it needs to get rid of formal charges. Okay, number of electron groups. There is a double bond counts as 1 electron group. The other double bond counts as a 2nd electron group, and a lone pair counts as my 3rd electron group. Therefore, I'm going to keep the same format here and just kind of retype. Instead of having 4 electron groups, the central atom has 3 electron groups. Therefore, it's sp2, and the sp2 always corresponds to trigonal planar electron geometry. Let's go back to our chart and show that. If you have 3 electron groups, then your electron geometry will always be trigonal planar. The options we're most likely to see is that the central atom either has 0 lone pairs, in which case the molecular geometry would be the same, or it has 1 lone pair, which causes the molecular geometry to be bent. And so if we go back to this, there is 1 lone pair on the central atom, which in this case is sulfur. Therefore, your molecular geometry and electron geometries are not the same, and your molecular geometry is bent. Structurally, what that tells us is that there's actually an angle here. This oxygen is coming off at about 120 degrees. It looks more like this. Let me rotate the lone pairs out a little bit. So this is actually kind of what sulfur dioxide looks like. This lone pair sits a little bit over here. We tilt it just a tad. Not that any of this really matters. Artistic preference. Okay, so notice how this compound and sulfur dioxide are very different. And it's just the nature of how geometries work. Okay, any more examples? I think I've got one more. XeF4. This is not a compound that you're ever going to encounter in the laboratory. It exists. It's really difficult to make because we're going to try to use a noble gas to build something, which is always a bad idea. So let's go ahead and draw that. So we're going to have xenon in the middle. I don't think there's a hotkey for xenon. There's not really a hotkey for xenon. I'll have to go in there and edit that. And then I'm going to put 4 fluorines on there. Fluorine, fluorine, fluorine. Not an organic compound because there's no carbon-hydrogen bonds anywhere. So let's go ahead now and think. It didn't red box me using a noble gas in the middle of a compound. This is hard to make. The only reason it works is because fluorine is so electronegative that it can pull electrons off of even xenon, which is a noble gas. Xenon as a noble gas has 8 valence electrons. So the number of total valence electrons that I have to work with in my structure is equal to 8 for the xenon plus 4 times 7 for the fluorines, which is 36 total electrons. 4 times 7 is 28, plus 8 is 36. So I have 36 valence electrons to place on this compound. I have already placed 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I have 4 more, so there's, oops, I don't like where to put it. So 34 and 36. So this right here is the correct Lewis structure for xenon tetrafluoride. The formal charges on this one, it shows a red box, so I should, this follows the Honk X rules. Halogens make 1 bond, have 3 lone pairs, and when they do that, they don't have a formal charge, so I'm good. Xenon's formal charge, remember that formal charge is equal to the number of valence electrons, which in the case of xenon is 8, minus the sum of lines plus dot. There's 4 lines plus 4 dots, so equals 0. So I don't know why ChemDraw is unhappy about this. It should have been upset about the fact that it was a noble gas in the first place. Okay, so there's my structure. How many electron groups do I have? 1, 2, 3, 4, 5, 6 electron groups. And so if I have 6 electron groups, then my hybridization is sp3d2. My electron geometry is octahedral. When you have 2 lone pairs, the molecular geometry is square planar. This is really a dumb example to give you because we'll never see this again in the context of organic chemistry. But perhaps, I don't know why I have this as an example. Maybe it was a throwback to the days that I used to teach Gen Chem and how much I enjoyed doing that. So 6 electron groups equals sp3d2 and octahedral electron geometry, and there are 2 lone pairs on the central atom, which in this case is the xenon, so the molecular geometry is equal to square planar. You don't have to remember that. You'll probably never see that again, and if you do, I will give you the chart. So here are the answers to the questions. The top 3, well 4 if we consider the formaldehyde that we looked at before, are important. The xenon is not really that important, but just kind of illustrates how we would use that chart. So I am trying to copy all of this. Let's see, new slide. And we'll just dump this in here so I can upload these notes for you. All right. Finally, let's look at just one more example and call it a day. What is the electron geometry of water? Well, water is H2O. I hate doing this, but I am going to use my mouse as a cursor, and it's going to be a mess. So be prepared for this. So water looks like this. We can use the Honk X rules to build water. We have H2O, and the oxygen has 2 bonds, 2 lone pairs. So there are 1, 2, 3, 4 electron groups. So that means I'm down here in this area. The hybridization of the oxygen will be sp3. The electron geometry will be tetrahedral, and there are 2 lone pairs, so my molecular geometry is bent. So that's the electron geometry of water was the question, so the answer is tetrahedral. Let's take a look at the homework and figure out where you should be with that at the end of today's class. Chapter 1 homework. Oops. You can't see what I'm doing on my other screen right now, and that's okay. Let's pull this over. Okay, so the last homework should have taken you through 8, 9, 10 right here. Yeah. Lewis structures through number 9. This question number 10 is not one that I have lectured about, so I'm going to come back to that before we end this video. and we'll talk about 10 and 11. Here, question number 12, number 13. Yeah, 12 and 13 are what you should be able to do based on the video that you're watching right now. I just realized there's one thing in this video I haven't shown you. Let's go back and look at that. It also asks to determine if the molecule is polar. So let's go back to these structures right here. Polarity is kind of a weird concept for organic chemistry because molecular polarity doesn't really exist. But in small molecules, you can think about them as having a molecular movement. What that means is this bond right here involves electrons being shared between a carbon and a hydrogen. And those electrons are not shared evenly. And so what ends up happening is carbon is a more electronegative element because it is closer to fluorine on the periodic table. And therefore, it takes more of these electrons than the hydrogen does. There are a couple of ways of diagramming that. Kind of the most precise way is to take the partial symbol and put a positive charge on it. This is partial positive. And therefore, the carbon is partial negative. And then this hydrogen right here is partial positive. Okay, so what this is showing is that there is a movement of electric charge from the hydrogens to the carbons. The problem is that when you use these partial symbols like this, is that now the carbon actually loses electron density to the oxygen. So the oxygen has a partial negative, and the carbon ends up in this bond being partial positive. Well, does the positive and negative cancel out? Well, we don't know. And the reason is because partial means it's an unspecified quantity. So it's somewhere between 0 and 1. So a positive somewhere between 0 and 1 plus a negative somewhere between 0 and 1 is not equal to 0 because you don't know what the values are. And so these partial symbols like this actually become less useful. And so one of the ways, and there's a hotkey for erasing all of this. I do not want to keep my ink. There we go. Let's go back. A simpler way of showing this, and I think the way that is more useful, is to just, whoops, not a laser pointer. I told you this would be messy. A simpler way is to actually just take and draw a positive charge on the atom that loses the tug of war for electron density, and then extend an arrow towards the atom that gains the electron density. We actually try to write the positive charge kind of in a way that allows us to extend that arrow in a straight line. So this is another way of showing partial charges. And this is actually a more common diagram. This is how I typically show partial positive and negative charges, is just by diagramming the flow of electron density. If you add these three arrows together and they tend to point in a general overall direction, then yes, the molecule overall is polar. There's a movement of electrons from one side to the other, so yes, this is a polar compound. If we go back to this compound right here, the hydrogens lose electron density to the carbon, and then the carbon loses electron density to the chlorine, and there is more or less a movement of electron density, so this methylene chloride is also considered a polar compound. In this case, carbon and sulfur are pretty evenly tied. The sulfur has a very slight advantage. So if you want to kind of draw that to scale, this is what the electron motion looks like from the carbon to the sulfur. The oxygen is much more electronegative than the carbon, so it pulls electron density on this side. And if you add these two arrows together, you would end up with something that still lean to the left-hand side. So this is also, by the definition of addition of arrows, a polar compound. Sulfur is less electronegative than oxygen, so it loses electron density in this direction. And these lines kind of shoot off to the side once in a while. This is why I hate using the ink function on my mouse. But because the molecule is bent, that means that there is more or less a movement of electrons from the sulfur kind of this way if you add those two arrows together. So this is considered a polar compound as well. This compound is not polar. The molecular geometry is square planar. I don't know where that went. Oh, I must not have copied that. The molecular geometry of this compound is square planar, which means that the xenon is losing electron density to all of the fluorines, but those four fluorines are sitting in a flat plane, and that means that they just kind of, if you add all these arrows together, these arrows right here offset each other and cancel out, and these arrows offset each other and cancel out, and we end up with no net polarity. It's kind of like a disk where there's positive charge in the middle and negative charge on the outside, And polarity is defined as having a clear division on a one-dimensional axis where there's a line, where there's positive on one end of the line and negative on the other. It is much more important in organic chemistry for us to identify points of polarity, atoms that individually are polar, and they're creating individual charges. So this compound right here, methylene chloride, is pretty useful in the laboratory because it has those points of polarity. The chlorine's partial negative charges make this a pretty useful solvent. And we'll look more at examples of that when we get into different functional groups like alcohols. Let's get rid of my, discard those. Okay, so let's go back to that homework assignment and talk about this question right here. This one kind of is self-explanatory. I'm going to see if you can figure that out without me. But let's talk about this. So this is a Lewis structure in all of its glory. It's beautiful. All the carbons are drawn out with their hydrogens. After a while, chemists are like, well, this is kind of boring. This is tedious, not boring. It's tedious because you have to continue to draw all the lines. So instead what they do is they draw a condensed formula. And in a condensed formula, they list all the hydrogens are listed immediately after whatever atom they're connected to. So I can just take this carbon and say, oh, it's got 3 hydrogens, so I'm going to write this as a CH3. This carbon has 2 hydrogens, so it's a CH2. And then the next carbon has 2 hydrogens, CH2. And then the oxygen has 1 hydrogen, so it's OH. So this is called the condensed formula. The other thing that we can do is we can go from this Lewis structure to a skeleton diagram. And in the skeleton diagram, if there is a hydrogen that is connected to a carbon, we just stop drawing it. And if there's a carbon, we just leave it as either an endpoint or a joint. So that's a carbon, and that's a carbon. This compound has 3 carbons because there's an endpoint and 2 joints. And this carbon has 2 bonds coming off of it. And since carbon always makes 4 bonds, the other 2 bonds must be going to hydrogens, and we don't bother to show that. So let's go ahead and draw on this. See if I have my drawing tool working now. There we go. Nope. There, maybe that'll work. Yep, okay, we got a drawing tool going. Okay, so here's the condensed formula, CH3, CH2, CHO. So that means that we have a carbon, and it's bound to 3 hydrogens. Hydrogen, hydrogen, hydrogen. Carbon always makes 4 bonds, so the next bond must be going to whatever atom is next. So that's a carbon. This carbon is bound to 2 hydrogens because they're immediately written after it. We look at the Lewis structure and say, oh, that carbon needs 4 bonds. So the next bond must go to whatever atom comes next in sequence. That's a carbon. This carbon is bound to a hydrogen. And carbon makes 4 bonds, so the next 2 bonds must go to whatever atom is written next in sequence. So there we go. Put our lone pairs on there because of Honk X rules, and that's the Lewis structure. The skeleton diagram just says that we're going to go ahead and get rid of any of these hydrogens. So I'm going to go ahead and I have a carbon, I have a carbon, I have a carbon, and then a double bond to an oxygen like this. And now what I need to do is draw it without the carbons. But it's kind of hard because I've drawn in a straight line. So if I just got rid of the carbons, it would look like this, which unfortunately kind of hides the number of carbons. So we need to kind of introduce some kinks in there and say, well, this carbon down here on the end comes up to that carbon right there, and then it goes down to that carbon, and then we have the oxygen coming off. So this right here is the correct answer for the skeleton diagram. There's a couple more of these. I'm going to go ahead and let you guys answer these on your own, but that's the concept of trying to get from Lewis structures to the skeleton diagram and also how to deal with condensed formulas. Before I stop the video, I want to make sure that I've hit all the learning points. So we draw correct Lewis structures. We did the heck out of that. Identify hybridization. That's based on counting electron groups around the center atom. We talked about electron and molecular geometries. And then we predicted molecular polarity on simple compounds. So I need to fix that to say on simple compound, of simple compounds. Somewhat, yeah, that works. Okay, that's it for today.